So today we're going to continue our journey through functional programming and talk about immutability. This is actually something you've been using since 115 to an extent. So let's talk about it and face this head on. Talk about what immutability is and what we mean about this. Today, you can actually do the second part of LT4, this read songs from file, which is the hard part. By the way, I'll say LT4, in my opinion, is the peak difficulty from the lecture tasks of this. I don't think LT5 and 6 are as difficult as LT4. LT4 does make you think in new ways. It really forces you to think in a functional programming way. And it can bend your mind. It can make you think a bit. For the read songs from file. Today's lecture is about implementing this add rating more directly. And add rating is quite a bit simpler. You know, immutability, there's some stuff that we got to talk about when it comes to this. But it's not too difficult. Read songs from file is where it's going to take you the longest time. Oh yeah, I forgot. I wanted to mention that in lecture. Don't join the office hour Zoom meeting during labs. I'm surprised I even have to say this. I thought y'all would just not do that because, to be honest, it's just flat out rude. People were taking a quiz last week, and other students are joining office hours and raising their hand, and like you wouldn't do that in an actual room. Why are you doing it in a Zoom meeting? We're going to crack down on that. I'm telling the TAs that they can just boot you right out of the meeting and put you to the end of the queue if you rejoin for office hours. The office hour TAs are going to put you right at the end, probably not even see you that day. Like, cut it out. Why do I even have to say something like that? It's ridiculous. Don't join a meeting where students are having a quiz. It's like walking into a room an hour before your lecture and just waltzing in and sitting down. Like, don't do that. Don't do that. Come on. It's a virtual space, but it's still a space. Like, respect other people's time, especially when they're taking a quiz. It's very distracting. Like, cut it out. We're going to crack down on that. And if you get mad at any TAs, don't get mad at a TA. You can take it up with me. I'll put you in your place if you're doing that and you're still doing that tomorrow. Anyway, so add rating. Not too hard, but we got to talk about immutable objects to be able to see how this works and how to do this. And then read songs from file. This is going to be the difficult one. I added a few lines just to make reading the file a little more clear. I read the file and put it into a list of strings with one string for each line, and then you have to write a recursive method to turn that into a list of songs containing all of the information from this file. Each line in this file is going to be in this format: a YouTube ID, artist, title, rating, and energy rating. Which is how energetic the song is. And each time you read a line, you have to parse this information and get it into your data structure in some way. So this has to be done recursively, like using a loop that we've been doing since week 1. Read the file, read each line, and update a data structure with a loop. But now, since you can't use var, you have to update that data structure using recursion. So each line that you read, you're going to have to make another recursive call to your recursive function and use those 4 ingredients for successful recursion. A base case, assume that your recursive calls are going to be correct. Design your recursive step under that assumption, and then make sure all your recursive calls get closer to the base case, where the base case, probably going to be an empty list, a file with no lines left to read. I'll give you that hint. And one of the tricks here is that once you read the YouTube ID, songs are unique on YouTube ID. Once you read a YouTube ID multiple times, you have to collect the ratings, the rating and energy rating, into objects of type song rating. You have to collect those into a data structure, a list for that particular song. So songs are going to be rated multiple times in this file. And if it's rated multiple times, you need to collect all those ratings in a single song object using the add rating method that you wrote in the first part of this. Autolab will not check your tests for this one, so you've already completed the testing in Autolab for this objective. That does not mean you should not write tests. For the love of everything, That does not mean you should not write tests. You should absolutely be writing tests. It just means that Autolab's not going to check your tests, mostly because you would have to create your own test files, and that just gets hairy, and then we're going to get all kinds of errors in Autolab because, you know, the files you submitted, and you did it in a weird directory structure or something. Or, you know, it's just a road I didn't want to go down. It's just asking for a lot of errors. So still write your tests. And I don't have much to enforce that with your grade, but if you come to office hours and you don't have tests and you're asking about LT4, the only thing, I'm telling all my TAs this, if I don't think I did explicitly, so TAs who are listening, spread the word, don't help that student. Like, if they come to your office hours asking about LT4 and they have no tests, they don't have a single test, not even a main method, ideally unit testing, but if they don't even have a main method and a test file set up that they're parsing, don't answer their questions. Like, don't waste your time. If a student still doesn't understand the value of testing at this point, this can be where they learn, where we teach them the value of testing. Write your test without being forced to. It's such a good development practice. It's how you're going to write good code when you're out there on a job. It's how you're going to not get fired from your job if you do get a job without testing your own code. If you get through all your coursework without writing tests, I'd be impressed. But once you get out there. Anyway, testing is freaking important. It's why we teach it so early in the curriculum. Unless your question is, how do I test this thing? That's the only question we're going to answer. I'm getting kind of, I don't know. I feel like I need to restructure something. Since so many students are doing this, I need to restructure something in the course to really get you to understand the value of testing. I feel like a lot of you are missing the value. If you're writing good tests, you shouldn't need office hours at all. If you're using the debugger, you shouldn't need office hours. You shouldn't need, that should replace a TA or myself. Anyway, write your tests even though Autolab is not going to force you to. This method is hard enough to write that you're going to benefit from testing. I couldn't imagine writing this method myself without writing any tests. That's a really tough task. If you're using Autolab as your tester, just writing code and submitting and seeing if Autolab says it's right, you're in for a long time. And that's when I get students saying, I spent 20, 30, 40 hours on this assignment. Well, I'm going to look at your number of submissions. And if you have 100 submissions, it's because you missed the point of testing. Anyway, I don't want to rant on that too long. It's just something that's been bothering me lately that I don't know. I think it's the way I test your tests that encourages that behavior. But anyway, let's talk about immutable objects. I don't want to rant today. Today's a good day. Immutable objects, in one line, the state variables cannot change. So we're completely away from the idea of objects having state. They do have state variables, but they're all values, and they cannot change. When our recovery plan's coming out, it'll be, so for point of sale, the recovery plan's just going to be an extension for almost everybody. The question is how long. And I want to get those out by tomorrow at the latest. The quiz and interview grades are posted, though, so you know what parts of the recovery plan you'll need. Are office hours still available for Pale Blue Dot? Nobody should be working on Pale Blue Dot anymore. I mean, you can ask if you want to ask questions and be like, "How was that supposed to work?" You know, that we'll always answer that. But nobody can get credit on Pale Blue Dot anymore. Okay, so the state variables can't change. That's immutable objects in one sentence. That's what they are. The state variables cannot change. They are all values. With val, not var. Other than that, they're just regular objects. They go on the heap just like any other object. But when we're passing these by reference, whenever we pass an object by reference, we're always concerned about the method that we pass it to or the function we pass it to, making changes to the state of that object. It's something we always have to keep in mind. That's why we talked about heap and references and all that. With immutable objects, we still pass them by reference, but we're not worried about the state changing because the state cannot change. So we don't worry about methods with side effects. And this is a big fundamental part of functional programming is that we can't have side effects. We have immutable objects, We have first order functions and all the and recursion and this good stuff. And immutability is a key crucial part of functional programming, in that state cannot change. It can never change. So we're not worried about any side effects ever, which is a very handy principle, very handy property to have, especially when you have like a distributed system and a lot of information being shared across multiple machines, multiple threads on a single machine, a lot of concurrent code running. And that concurrent code doesn't have to worry about state changing if you have immutable objects. You don't have to worry about this machine over here changing your data structure while you're working on it, which would be a recipe for bugs. We don't worry about in that functional programming because we just say everything's immutable. So what if we do actually want to change an immutable object? This seems like a huge restriction to have. We have an immutable object, its state can't change, but we have a situation where we want its state to change. What do? We have a song, and it has 1 rating on it, and we want to change that song. It's immutable. It's an immutable object, but we want to change that song to add a new rating once we read a new line from that file that rates that same song again. How do we change that thing? Like, that's ridiculous. We can't change anything. Yeah, Jesse spends 3 weeks on a subject and literally says, don't use that anymore. True. I mean, it's true. Not use it anymore. I'm just saying don't use it for 3 weeks. And then after these 3 weeks, you can use whatever you want. But I want to show you both I have to. It's part of what 116 is. But I have to show you both these paradigms, OOP, and FP. That's fundamentally what 116 is these days. So let's take a look at an example. Here's an immutable class, which is going to be used to create immutable objects, called immutable counter. I'm doing some artificial stuff here. This isn't something, like, you wouldn't set it up completely like this. You could still get immutability and the benefits thereof without doing everything that I'm doing, specifically not allowing access to the state variable. But let's take a look at this class. I have the state of this object is only one state variable, counter of type int, and I didn't use val or var here. So as we know, that's going to be a val, but it can't be accessed from outside of this class. So if I have another class that has a reference to an immutable counter, it cannot do .counter. This is invisible to the outside world. It can only be accessed from inside this class, or inside objects of this type, inside this class definition. So this is an immutable object because all of its state variables cannot change. None of the state variables are var. So how do we actually change things? When we want to make a change, we're going to create a new object of this type with the change applied to it. So this class is a counter. It just stores one int, and we can increment or decrement that int and print it out just so we have some way of looking at it, at what that int is. That's all it can do. The fact that Scala is based on JavaScript is what hurts me. Scala is based on Java, not JavaScript. I see where you're coming from, though, because you've seen JavaScript and Python, and this is more of a JavaScript flavor than a Python flavor. I see what you're saying. Never mind. So immutable, I see where you're coming from with that. So this immutable counter is going to track this one value, increment and decrement. If we want to increase that value by 1, we want to increment the value stored in counter. What we're going to do is create a brand new immutable counter with the change applied. So we take counter plus 1, whatever the value of counter is, we're going to increment it and create a brand new immutable counter with that incremented value as its value of counter. And then we're going to return a reference to that brand new object that we created. So whenever we want to make a change to an immutable object, change its state, we're not going to modify the object itself, but we're going to create a brand new object with the change applied. This is the fundamental concept of immutable objects. We'll create a brand new object with the change applied. In your interview, you're going to get a question next week that something like, what if we want to change the state of an immutable object? Create a new object with the change applied to it. You can pretty much guarantee you're going to get that question because that's like the thing about immutable objects, and probably something about what is an immutable object. There's really not much else we can talk about. That is what an immutable object is. The rest of today's lecture is just examples of that and implications of that. So that's what an immutable object is. The state can't change, and whenever we want to simulate the state changing, we create a new object of that type with the change applied. Clip it, don't attack me. I will attack you, priest. Clip it yourself. I don't know. I see that so often. It doesn't really irritate me. I just wonder. Like, someone clip that. You have that capability yourself. Serve me. It's hard to not read it like that. I don't think that's your intent, but... And I wasn't going to say anything until you said, don't attack me. I'm like, well, I have to now. But yeah, somebody should probably clip that. It would benefit the class. I could say that because I'm a little busy right now. So that's what immutable objects are. The state can't change. Jesse bullying students. Not bullying students. I'm bullying priest. There's a difference. I'm bullying one particular student. And whenever you want to change, now that made it in the middle of my summary. All right. An immutable object, the state can't change. And whenever we want to change the state, we're going to create a new object of that type with the change applied. So here we have a counter, can't change. If we want to increment or decrement the counter, we're creating a new counter with the change made to it and then returning a reference to it. Let's see this in action. And I want to expand this a little bit. So we can call increase or decrease. And whenever we call that, we have to assign the output to a new variable of type immutable counter. But let's take this to the next step and say, well, what if we want to increment 20 times? Or any number of times? This is where we're going to pull in some recursion. That's going to help us be able to do that. So you can think about this for a while. How would you... and since we're not returning... We can't return unit in an immutable object anymore. Like here we do because we're just printing to the screen. This does have a side effect, I guess. But we always return something, which is the new object with the change applied to it. And then we have to use that return value. We have to use that somewhere or else we don't get to see our changes. So you can think about this a bit. How, using this class right here, say you had an object of type immutable counter, and you want to increment 10 times, or 20 times in this example. How would you do that? Or generally n number of times. How would you do that? So there are a few things that we could do. If we had access to counter, we could say immutable, we could say counter, we could say new immutable counter of counter dot counter plus 20. That would be the easy way to do it if I didn't artificially restrict this. If we had val right here, we could do that and we could do that just fine. But we don't have val there. We don't have access to counter in this. This is artificial. You wouldn't actually do anything like this. I just want a reason to use some more recursion. So I can show you another example of recursion. So we don't have access to counter, so we can't do it that way. We could do this in a loop. And we could have var counter, immutable counter equals new immutable counter. And then in a loop, call increase and loop 20 times. And each time we call increase, we would say counter equals counter dot increase. Do that 20 times, and then we have our incrementing done. I've also artificially restricted that by banning var for this learning objective. So since we can't use var, we can't use a loop and use reassignment. So that's off the table as well. So what's left? Good old recursion. So let's see how to do this using recursion. And see how we're going to take a counter and increment it n number of times. In this example, 20. And let's look through our steps of the recursion. This is my last slide, right? Let's look through the steps of this recursion. We need a base case. That's a trivial input-output behavior. So first, I should talk about the setup first. So I'm going to write a method that's going to take a counter and a value n and return a new counter that has the value of this counter, but incremented n times. Hey, no rebellion. I don't want to. I don't want a mutiny. Actually, if you have a mutiny on me in a rebellion, do I get to start my summer break earlier? Because I don't know. Actually, I might be a fan of that. So we're going to start with our base case, a trivial input-output behavior. If we have a counter and we want to increment or decrement it 0 times, n is already 0, well, we're just going to return that counter because there's nothing to do. We're already done. So just return the counter if n is 0. Done. Else, we have to do our recursive step. So in our recursive step, we're first going to assume that our recursive calls are going to be correct. And we're going to base all our logic around that. So if n is less than 0, and we're going to handle negative and positive numbers here. So if you give this negative 20, you're going to say, I want to decrement counter 20 times. So if n is negative, we're going to call update counter, make the recursive call, and then change our parameters in such a way that our logic is going to be sound and we're getting closer to the base case. So update counter, our recursive call. If we say n is negative 20 here, actually let me use the positive example because it'll be more clear with our example here. So if it's negative, we're gonna decrease and increase n. But if it's positive, let me explain it through the positive example. If we make a recursive call for n minus 1 and then call counter.increase, counter.increase is going to return a new counter with the state variable incremented by 1. So we're going to increment counter by 1 and then decrease n by 1. So we've fulfilled one of the increments that we need. We've incremented counter once, and then we're going to say, hey, I've incremented this once, but it's still going to need n minus 1 more increments. So like when n is 20, we get a counter, we increase counter, and let's say the counter is 10, we'll follow this example. The counter is at 10, we're going to increase that. This returns a new counter with a value of 11. And we're going to say this counter with value 11 still needs to be incremented 19 more times. We're going to assume that this just returns the right counter. So if this is correct, which we're assuming it's correct, then update counter of 19 on a counter that has already been increased to 11. If that returns the right answer, well, that's just our final answer, and we're returning it. It's the last expression in the method call. And then we're done. Oh, and the recursive call is the fourth step, the fourth ingredient. The recursive calls have to get closer to the base case. If n is positive, we're decrementing 1 by 1. If n is negative, we're incrementing by 1. So we're always getting closer to 0. Since these are integers, negative integers, we're increasing. Positive integers, we're decreasing. So we're always getting closer to 0. So we have all our ingredients to good recursion. So this is going to work. We got our 4 ingredients. We mixed them together in this method, shook it up, compiled, hit run, and it works. Strings are immutable. They have been your whole life. Since you were born at the beginning of 115, strings have been immutable. So let's talk about it. Always has. Always have been. Yeah, it's definitely an astronaut meme there. Strings are immutable? Always have been. So let's take a look at this example where we're going to be using some strings and floating strings around. And you'll notice today's examples will be strings and a list. And you'll notice that I was very careful to not use strings or lists last time we talked about stack and heap, because they behave quite a bit differently than other objects on the stack and heap. So let's take a look at this example. We're just going to play around with some strings, call some methods, and we're going to track what's going on in the big return of the stack and heap. We're going to track the stack and heap and talk about what's going on in memory as we trace through this program. So I'm going to skip some of the things, or rather just give a quick overview of the things that you should already know. We're going to start at the main method. We're going to create a value named course. We're going to assign it the value of a string. And strings are not in that list of primitive types. They do extend any ref, not any val. So strings actually go on the heap. So this string that we created, containing the characters CSE 116, actually goes on the heap, and it's going to get some reference. I'm just going to use 1, 2, 3, 4, and 5 in this example. Spoilers, I'm going to put 5 things on the heap. So this string, this syntax, which we call a string literal, is going to create a new object of type string, put it on the heap, and return a reference to that string. So we get a reference to that string on the stack in a variable named course. Now we're at the point where we're calling nerf of course. So nerf gets course, which is the reference at 1. It is not the string CSE 116. It is the reference at 1. We're all comfortable with that from LO1. This is going to get the reference at 1 in input. And then we're going to call input.replace, which is going to replace all instances of 6 with instances of 5 in this case. What replace does is creates a new string with the change reflected. Strings are immutable, so this string can never change. By the time I'm at the end of this example, this string is still going to be sitting here completely unchanged. Any reference to that string is always going to be CSE 116. So I'm calling replace 6s with 5s. What this does is create a brand new string with the change applied. So we get a new string on the heap at a different reference with the change applied. All the 6s are replaced with 5s. This method returns unit, so it doesn't return anything. When this method is over, the stack frame ends, we lose that reference at 2, and we move on with our lives. So we created a string on the heap that was the output of this method, but we never returned anything. We never used that new reference. We never used the reference to that new string. So after this method call, we don't even know that this string exists. Course is still a reference to 1, which is still and always going to be CSE 116. And this method had 0 effect. We returned unit when we're working with immutable objects. That's always going to do nothing. It just doesn't do anything. I shouldn't say nothing. I just had an example where I used a print line and printed something to the screen. But it's not going to change the state of the objects. It's not going to change the state of the stack and heap. Well, I guess it did change the state. It's not going to change the state of the stack. It's not going to change anything. So we can never access this again. This is just wasted memory. And it's a strong candidate for garbage collection. It'll probably get garbage collected very quickly. So let's move on to something that's actually going to do something. Let's call this method amplify. We'll put a new frame on the stack. That takes course. That's a reference at 1. That's the CSE 116. And we're going to call replace again. We're going to replace 116 with 250. Replace creates a new immutable object with the change applied. So we get this new string that I'm going to say it's at 3 for the reference. And this one actually is returned. We have return type string. So this is going to be returned from the method. And furthermore, we're going to store it in a variable on the stack. So we return this reference at 3, and we're going to store it in this data structures variable with a value at 3. There's reference 3, which is a reference to this string right here. So now we actually do get to see a change from this method. This is I'll explain on the next example. And for those of you really paying attention, technically there are a lot more strings being added to the heap. Wherever I have a string literal, there will be a string 6, a string 5, 116, 250, is great, is fun. All those will actually be on the heap as well. But I didn't add them all to this slide because I'd have strings all over this slide. Maybe I should just to really drive the point home, but we don't have references to any of those strings anyway. So here's a line. This is a common mistake that we see a lot in 115 and sometimes in 116 is we're going to compute something and using an immutable object, and then how I usually call it is we just walk away from it. So we compute a new string. What this concatenation operator does is creates a brand new string. It doesn't make any changes to these strings that were created, but it creates a brand new string with the concatenation and returns a reference to that string. We have to do something with that new reference or else we lose it. So here we're computing a new string, this string at 4, and then we're just walking away from it. We never store a reference to it. We have no way of accessing it anymore. We just walk away from it, and we just wasted our time. We wasted some CPU cycles. We wasted some memory. Now the garbage collector has to come and clean this up, clean up our mess. And we don't get to see any changes. This string, we never get to see in our program. We have no way of accessing that. Really pointless. What we have to do when we're working with immutable objects is reassign or assign the output to a new variable. So here we're going to do something very similar. We're going to create a new string. It's going to go at 5 in my example and get this string that's the result of the returned reference from the concatenation operator. And now we're actually going to store it in a value named course string. We're actually going to put it on the stack so we have a reference to it in this course string. And now we can actually do something with that. If you don't have the assignment here, if you just have the concatenation, it's not going to change your strings because your strings are immutable. They cannot change. Your strings can never, ever, ever change. They cannot change. But we can create new strings based on the strings that we have and then assign them to new variables. Or in the good old days of 2 weeks ago, you would use a var here and you could reassign a variable to the new string that's created. And then we can print them out to the screen, and we get these strings. And these two strings we don't have any access to. And also all the other strings that were created, we don't have access to those. They're candidates for garbage collection. They'll be destroyed since we have no way of accessing them anyway. Strings are immutable. Guess what else is immutable? Lists. And this is a more common mistake that we see in 116, is that you append something to a list or prepend something to a list and never reassign it to a value or a variable. Assign it to a value or reassign it to a variable. If you don't have an assignment, you don't see that new value that you just added to your list. Map is immutable as well. I should mention, there are mutable versions of these data structures in Scala, but the defaults are immutable, and especially since we want to talk about immutability in this class, I just stick with the default data structures. The mutable ones are banned for the homework anyway, so don't get ideas with that, because obviously they're banned. So let's take a look at this this beast of a code, this beast of a method. We'll step through this, one line at a time. Right, we got 15 minutes. We'll get through this one. But this is, by the way, this is to address the complaint of lecture examples are always super simple. Then you ask us to do more complicated stuff. So just like on Monday, I had a more complicated example. This one, again, this one is much more approachable than Monday's, in my opinion. Maybe you'll disagree. You should be able to follow all this code, and in fact, you should be able to. My expectation is that you could write this code. Granted, it will take you a bit of time, but you can read through this code. It'll probably take you a little while to really read through it, and this one right here is definitely going to take you a bit to, no pun intended, but unfold to be able to figure out what this one is doing. But let's step through this. I'll give you the high level. The high-level self-comment here is this is going to find the first n primes for n. So if n is 3, this should return a list containing 2, 3, and 5, the first 3 prime numbers. So, and this is directly associated with your LT4, where you have to write a recursive method that works with lists. How do we do that? How do we collect values in a list when lists are immutable and your professor banned var? How do you do that? So let's bring back the stack and heap and talk about it. Let's have a conversation about it. So we're going to pick up at the base case. So we're going to say that I want to find the first 3 primes, so we expect this to return 2, 3, 5. In any order, this would be, your testing list applies to, you'd sort and then compare, or find some other way. I like sorting and comparing. I think that's the easiest way. But we want to find the first n primes, then I'm going to print them all to the screen just in this method. So we have this call. We're going to look at our recursion. We have 2 base cases here. If the value is 0 or negative, we're going to return the empty list because nothing else really makes sense. What are the first negative 5 primes? I don't know. What are the first 0 primes? An empty list. So that's one of our base cases. Another base case is n equals 1, which is where we're going to pick up execution here. If n equals 1, that's my trivial input-output behavior. I know the first prime is 2. And then we're going to have our recursive step, which I'll explain in a second. But the recursive step is going to include a recursive call with n minus 1. So if we look for our 4 ingredients for successful recursion, we have a trivial input-output base case. We're going to assume that our recursive calls are correct. And then the rest of the logic that we'll go over later, our logic is based on the assumption that we'll have the first n minus 1 primes. And then our recursive calls have to get closer to our base case, which we have. So we know we have 3 of the ingredients here. The question is my logic sound here? That's the part that we'll have to think about a little bit. So let's pick up execution at the base case. Without knowing what the rest of this method does, we know the recursive step is going to immediately make a recursive call with n minus 1. So we get our input of 3. We make a recursive call with 2. We make a recursive call with 1, and then we hit our base case, and that's where we're picking up execution on our stack and heap. Priest, I had these slides already. Like I did these several semesters ago. It wasn't your fault that I did that. It's the echoes of hundreds of students who have had that same complaint in the past echoing in my mind. I said, you know what? Let me just do harder examples in lecture then. It's a pretty simple solution. Fine, you can have the credit. So we get to the base case. Okay, I'm asked to find the first 1 prime. That's just 2. I'm going to return the list. Notice that in the base case is the only time where we're creating a new list in this code. And this is common with recursion. We saw it on Monday as well. The base case is the only time we're actually creating a brand new list. We have some trivial input-output behavior. I'm going to create a new list with the answer in it. Everywhere else, we're just appending the list. So when we return up the recursion, that's actually where we're going to be appending, or prepending in this case, new primes to the list that we created in the base case. So we've created a new list. We've added that to the heap. Lists are immutable. They're objects. They go on the heap. We get references to them, and the list can never change. So we have this list, which has only the value 2, and this list is going to be here forever. It's going to be here for the rest of my example, assuming it doesn't get garbage collected, which it doesn't in this example. So that is what's returned here. On our first, that arrow should be down a little more. Where should that arrow be? I don't like where that's pointing. But that's going to be returned from the base case, and we're going back to this call. This is where we were in this stack frame where n equals 2. We called first n primes of 1, and now we just got this return value. We're going to put n minus 1 primes at 1. It's going to be this reference to this list here. I'm going to compute the max prime. Here, I'll get into the logic of what I'm doing here. I'm going to compute the maximum prime that I have. So, n minus 1 primes, give me the highest value prime you have. Max prime, in our case, is going to be 2. There's only 1 prime. There's only 1 answer. It can be. And then we're going to make this recursive call, or not recursive yet, but a recursive function, find prime, which I'm going to take the next candidate prime. So the maximum prime that I found plus 1, that's the next possible integer that could be a prime. Of course, we know in this case it is going to be a prime 3. It's going to be a prime. This is the next possible number that can be a prime. And then I'm going to give it the list of primes that I've already known. I want find prime to take this candidate prime and then keep checking from this one onward until it finds the next prime, given that these are the already known primes. Once it finds the next prime, I'm going to prepend that to my list of primes and then return that list. Hopefully it's the list 3, 2 in this case. So find prime, we're going to put that frame on the stack. We're going to check this conditional. I highly encourage you to think about this, stare at this for a bit until it completely makes sense. If this makes sense to you, you're well on your way to completing the genetic algorithm. And it's not too complicated. It's an application of fold left, which we saw last Wednesday. So what I'm saying here, I'll just read this in English. I'm going to say if there are no known primes that are for which I is divisible by that prime. So if I, the candidate prime, is not divisible by any of the known primes, then that's a prime number. If we started at the max prime plus 1 and we keep incrementing, which we do here, and we find a value that's not divisible by any known prime, we know that's the next prime. If it's divisible by any of the primes, then it's not prime. It's a composite number, and we'll hit the else, which is check the next number. And keep checking numbers until we hit the base case. The base case is the next prime. If we keep incrementing integers by 1, we'll find the next prime eventually. What the hell does, I almost just read it is English. The pipe is a logical OR. So the accumulator variable, which is initialized to false, or I is divisible by the current prime that we're considering, which is modulo that prime equals 0. That means it'll be divisible by it. So if this is true for any of the primes, those are all going to be ORed together, so the whole statement is true, and then we're going to hit the not on there. So this entire expression is going to be false if I is divisible by any of the known primes. If I initialize that to false, then once I hit any true, this is going to be true. But if this is false for all known primes, I got myself a prime number, and this is going to be false, because false or false or false or false. It's going to be false, and then hit it with the not. It's going to be true, and I'm just going to return I. That's the next prime. In this case, I is 3. Known primes is a list just containing 2. 3 is not divisible by 2, so we're just going to return 3. Done deal. Didn't even have to hit the recursive step. We were in a base case already because we were looking at a prime. We had a prime on the stack in I. 3 was a prime. Done deal. And my code works, so it's going to return that 3. So we're going to take that 3 that was returned, we're going to prepend it to n-1, and this is the last expression in this method call, so that's what's returned. We're returning a list of ints, which is the list at 1. We follow our stack and heap at 1, and then prepend the value 3 to it. That's going to create a brand new list. So we have to do something with that list. We can't just let it go. And in this case, it's the return value of our recursive call. We're going to create a brand new list. This creates a new list. That gets added to the heap, and we have a list containing the values 3, then 2. And that's what we're returning in this stack frame. So we give that list back to this stack frame where n was 3 and waiting on this method call, this recursive call. This gets 3, or n is 3. This should be gone, right? What was I saying on this slide? Oh, yeah, just a reminder of why we're doing immutability. So this list will never change. So anything that has a reference to this list doesn't have to worry about the data changing, no matter what happens, because this list is immutable. So we get back to this stack frame. N was 3. n-1 primes. This returned at 2. This list 3, 2. And then our max prime, the max value from this list, is going to be 3. So our max prime is 3. And then we're going to enter our recursion again on find prime. Max prime is 3. So max prime plus 1 is going to be 4. We know that this is not prime, so we hope that this fails and we hit our recursive step. We're going to hit false or 4 modulo 3 equals 0. This is going to be false. 4 modulo 3 is 1, not equals 0. So our accumulator is false, or on the next prime 2, false or 4 modulo 2, which is 0, equals 0. This is true, so that's going to return true. We're at the end of the list. Our fold left ends. True, the not makes it false. We hit our else and hit our base case. 4 was divisible by 2, so we're hitting our recursive step, not our base case. Find prime, let's just check the next value. That's going to be 5. Well, that's not divisible by 3 or 2. 5 modulo 3 is 2, not equals 0. So false or false. Then false or 5 modulo 2, which is 3, does not equal 0. So that's false, false, false or false, false. Not, okay, now it's true. Now we return I. 5 is returned from that recursive call. That is returned. The next method was waiting right here. This stack frame was waiting right here. If that frame is put on the stack, it actually won't be due to compiler optimizations. This frame actually won't even be put on the stack. These frames will be combined into one due to tail recursion. But if that frame is put on the stack for our purposes for education here, that's going to return 5 to the other frame. That frame is going to return 5 back to this frame. We get 5 right here. Prepend that to our list at 2. N minus 1 primes, N minus 1 primes at 2. That's this list. 3, 2. Prepend 5. That creates a brand new list on the heap containing the values 5, 3, 2. And that's ultimately what's returned from this method. This reference at 3, which is this referring to this list. That's what's returned to our main method. Our main method gets that list at 3 and then prints them all to the screen. It's my last slide, right? No. Print it to the console. This is the last slide I want to talk about. In 1 minute, perfect. Anyone else just lost? I'm following what's going on. I don't know about anyone else. This is one where you're going to have to rewatch the VOD. I mean, there's just... I'm really relying on your understanding of everything that's happened up to this point. If you're not solid on stack and heap, you know, you're not going to be able to follow this. If you're not solid on how lists work in general, you're going to be caught up on prepend. If you're not caught up on what happened last week, you're going to be like, what the hell is fold left again? What is that? You really have to understand everything that's leading up to this. So this is a good lecture to use to brush up on everything else. Make sure you're solid on everything leading up to this point. This is a good aggregator lecture that's taken all the things to put together. If you're following this lecture on the first watching, you're doing great. That means you're caught up with pretty much all the topics. I used a lot of topics here. We have we have classes, stack, heap, all kinds of stuff. Anyway, I want to motivate the next topic too. We're even going to talk about the next topic. I visualize this by saying that these are 3 lists with, a list of 5, 3, 2, a list of 3, 2, a list of 2. That's actually not what happens in the heap. And when we talk about linked lists in 2 weeks, we'll talk about how this is actually represented in the heap. But this, I'll give a very quick overview right now. This, and these aren't garbage collected, by the way, and I'll explain why. This list actually only contains the value 5, and then stores a reference to this list, which only stores the value 3, and then contains a reference to this list. So this list has 5 and refers to this list, which has 3, which refers to this list, which has 2. So these actually don't get garbage collected, and we're actually reusing memory. Where each time we prepend to this list, we only need space for the new value and a reference to the next value. So we save a lot of space. The same is not true when we append. It's only true when we prepend. And when we talk about linked lists, that's my advertisement for linked lists, we're going to explore why that's the case. And then 5, 3, 2, print to the screen. And back to our lecture question.